It's a real pleasure to introduce the speaker today. This is the second in this year's series of Presidential Fellow Lectures hosted by the Presidential Fellow Society at MIT. The idea is to have a series of lectures that to bring together graduate students and faculty colleagues from across the institution to share in some of the exciting research and issues that are being of scholarship that are being undertaken on the campus. And it's a real pleasure today to have Bob Langer from the Department of Chemical Engineering as our speaker. Now, Bob graduated from MIT with a PhD in chemical engineering in 1974. He did a postdoc at the Children's Hospital with Judith Falkman thereafter, and then came back and joined the faculty here. When you look at Bob, you will not think that just looking at him and thinking about 1974 is, in my time, not very long ago, what he has accomplished in the years at MIT. If you read Time magazine or other popular press, you'll see words like father of modern drug delivery associated with his name. He has invented methods for delivering large molecules through membranes into the body. And he'll talk about many of these techniques today. He'll also talk about the applications and impact of the work, which is as dramatic as the science and engineering. He has won an enormous number of honors for his research, innumerable honors from professional societies. I think one of the most outstanding tributes to his work is he is currently an active member of all three national academies, the National Academy of Science, the National Academy of Engineering, and the Institute of Medicine. I may be wrong, but I believe Bob is the only active member of all three academies. He's also won the Lemelson Prize for Innovation based on the impact, both in a societal way and a commercial way, of his many research accomplishments. He holds over 400 patents as well. Most recently, you probably saw the press that Bob was awarded the Draper Prize. The Draper Prize for Engineering, awarded by the National Academy of Engineering. Engineers would like to think of the Draper Prize as our version of the Nobel. And if you look at the people who have come before Bob, and you look at their inventions, you would, I think, resonate with that idea. The inventors of the jet engine, the developers of Fortran, probably the first modern computer language. Now, some of you may curse these people, but the developers of Fortran, the developers of modern catalysts in petrochemical engineering. So Bob is an incredible company there. Beside all of these things, Bob is an extraordinary human being. He has one property that has gotten him in trouble once again, is Bob never says no, ever. And he's here today to deliver the lecture, Biomaterials and How They Will Change Our Lives. Bob?
Bob, thank you very much. It's really a pleasure to be able to speak with you today. And what I'd like to do is tell you about some of our research. Whenever I talk about our research, people would always tell me that I'm talking about the future because it's so far off. But what I'd like to do is tell you about how we've tried to use materials to deliver drugs to our bodies, sometimes to very specific sites in our bodies, which might lead to new kinds of medical treatments. And towards the end, I'd like to actually tell you how you can actually apply some of these approaches with materials to actually create new tissues in the human body. So the first thing I want to do is tell you a little bit about this field of drug delivery. A couple of years ago, I got asked actually to give a lecture to graduate students at the University of California at Berkeley. And I wasn't really thinking that much. And the way I started the talk, I said, probably everyone here has probably taken drugs. At some point or other. That's what they all did. They all laughed. But what I meant was that they'd probably take an aspirin or things like that. And the problem is that whenever you do take drugs of any type, the drug level starts out very low, it rises over time, reaches some type of peak, and then goes down. So several hours or a day later, you repeat the same thing. But the problem with that type of delivery, which happens for all drugs pretty much, is that those peaks can be unsafe, and those valleys, the drug's not effective. And the consequence of that's profound. Side effects from taking drugs, even the way you're supposed to, can cause many, many deaths every year. The Journal American Medical Association estimates that over 100,000 deaths each year occur because of these kinds of adverse drug effects, often caused by this type of way. So if you were able to deliver drugs at a steady, controlled rate to where you want to, the hope would be that that could have a profound impact on human health. And actually, I think already, even though it's a very young field, I believe it's already doing that. If one looks at this from a purely economic standpoint, in 1980, the sales of advanced drug delivery systems, which I'll be talking to you about, would be about $0. But if you look at last year, 2001, in the United States alone, the sales of these types of delivery systems exceeded $20 billion. So it's actually moving quite quickly. And that's, so what I'd like to do today is tell you a little bit about this field and maybe some of the things you might expect to see sometime in the future. Let me see if I do this right. Now, I've never used this computer presentation before, so do I just press this thing? Where? No, I do. Oh, it's up. Geez, okay. Yeah, usually I do this, and I got the pleasant surprise today that I was going to have a much more efficient presentation for you. So anyhow, this is an example of a controlled drug delivery system. It's a nitroglycerin patch. It delivers nitroglycerin over 24 hours. And so this is kind of a one-day system. It was one of the earliest ones to come out in 1982. But over 500 million of these were used last year. And you can actually, one of the great things about chemical engineering is you can employ principles like slow diffusion, even through very tiny systems. This is a graph of a system known as the NOR plant. And what you can see is these systems are the size of matchsticks. Yet, by slow diffusion through silicon rubber, you can get release for over 5 years from a single implant, and then you remove it. Well, I'd like to actually now go back in time and tell you a little bit about how I got interested in this field. And as Bob mentioned, after I graduated from MIT, I went to work with Judah Folkman at Boston Children's Hospital. And really, when I started this work that I'm going to talk about, it was pretty basic kind of stuff. I was studying this process of how blood vessels grow in the body, and I was trying to develop assays, bioassays, to study that. But these processes would take a long time, like 30 days. And the problem is the molecules we were studying were often large molecules, and they were destroyed rather quickly in the body. So what I became interested in doing to develop these bioassays was seeing if I could have a way to slowly deliver these macromolecules. Now, in 1974, when we started this work, I don't think really, other than that field, anybody cared. But what happened is, just about 4 or 5 years later, we'd see the whole advent of biotechnology and genetic engineering. So for the first time, it became possible to produce large molecular weight drugs, peptides, proteins, and so forth. And these drugs pose very serious drug delivery challenges. You couldn't swallow them because they were so big, very hard to take through the skin because they're so big. And if you injected them, what you'd often see are very short lifetimes in the body. But if you wanted to use one of these types of drugs on a chronic basis, it would be critical to have a way to deliver it in an unaltered form and yet protect it from harm. Now, when we started this work, the conventional wisdom in this young field was that you couldn't really get large molecules through biocompatible polymers. In fact, in the 1970s, when you look at quotes, and I'll just show you this one from 25 years ago, when people were describing this young field, which was then largely in the research stage, this is what they would say. And I'll just read this to you. It says, it's a direct quote, it says, "The agent to be released is a small molecule with a molecular weight no larger than a few hundred. One would not expect that macromolecules, for example proteins, could be released because of their extremely small permeation rates through polymers." Actually, this quote was very helpful to us in getting some of those patents that Bob mentioned. I spent several years in the laboratory And I was able to find that you could take certain very hydrophobic polymers, polymers that absorb very little water, and by dissolving them in the right kind of solvent, adding powdered drug, and doing this at a very low temperature, we could make little microspheres. Here's one cut in half. And by using these approaches, what we were able to show is that you could get the release of a variety of different molecules, peptides and proteins, ranging in molecular weight from 14,000 to a quarter of a million for over 100 days. Now, in these early studies, you can see that the release rates weren't constant. So we used some chemical engineering modeling approaches to figure out why this was, and we were actually able to construct microspheres that could get us absolutely constant release. And this is an example of that, where we're releasing albumin for over 50 days. When I first started doing my work, you know, I mean, now I think this is about the 7th or 8th talk I've given this week, and but the thing is when I first started my career, I was not a good speaker at all, and I was very scared actually of giving talks. And the very first time I got asked to talk at an international meeting was in 1976 when I was a postdoc, and it was in Midland, Michigan. That's where Dow and Dow Corning is. And I was actually quite nervous about it, so I stopped actually work about 2.5 weeks before the talk, and I kept practicing my 20-minute talk over and over again into a tape recorder. So finally the day came, and that was, like Bob said, 26 years ago, so I was quite a bit younger than I am now. And I was giving this talk to this, pretty distinguished audience of more elder polymer scientists and engineers. So I got up and I gave the talk, and actually at the end of it, I actually felt pretty good about it. I didn't forget too much of what I wanted to say. I didn't stammer too much. And so I thought when I was done with this talk that this, kind of more older scientists, being nice people, would want to encourage me, this young guy. So when I got done, though, a whole bunch of them came up to me after the talk, and they said, well, we don't believe anything you just said. It was kind of my introduction to how scientists sometimes interact with other scientists. At any rate, it wasn't until another 3 years later, 1979, that a variety of groups, like at National Institutes of Health and other places, repeated what we'd done, and then the question shifted to how could this possibly happen? So Rajan Bawa, one of my graduate students, started taking techniques that were normally used in pathology, like using a microtome, and he would cut thin sections through these polymers, and we would visualize them. So here's a 5-micron thin section of one of the polymers we used, ethylene vinyl acetate. And if a molecule was 300 molecular weight or greater, it could not diffuse from one side of this to the other. But if you put a protein in, like here's a reddish protein, myoglobin, if you put that in and you cut a slice before any release, what you see is what we call a phase separation, where the polymer's here and the protein's here. Now, if you take one of these systems, millimeter thick system, and release it, say, for a year, and then cut a thin section, what you see is left behind where the red protein was are these pores. And clearly, it's the way we've made these that enable these pores to occur, because you didn't see it 2 slides ago. But it turns out that these pores, you can do a lot of microscopy on it, these pores have a lot of tight constrictions in them, and they're also incredibly winding and tortuous. So it takes a very long time to get through. One way I explain this to people around the country is it's kind of like driving a car through Boston. Boston has a very high tortuosity, and so if anybody's ever been there, they understand. Now, it turns out we've also done a lot of work kind of modeling these systems and understanding how to regulate the kinetics of these systems. And it turns out that by manipulating the pore structures, you can take very, very tiny systems and get your release almost anywhere from a day to several years. In fact, the biggest problem that I have found as a professor in getting long-term release actually turns out not to be the design of these systems, but rather my ability to find a graduate student who will do the experiment that long. And actually, it turned out in the 1980s, I had a very good graduate student named Mark Saltzman. And he actually did this experiment for over 3 years. And then one day, for his thesis. And then one day he came up to me and he said, Bob, I've been thinking. He said, what will I do if this experiment fails? He said, do I have to repeat it? So we stopped at 3 years and 2 months and 5 days. But I've always thought with the right student, we could probably go 6 or 7 years. That's not to scare anybody. But, and actually, it turns out to be a good story. Mark actually had gotten an endowed chair at Cornell, and now Yale just recruited him to head up their bioengineering program. Now, one of my goals also has been to not just do the research, but we wanted to really try to see the work have an impact ultimately in people. Some of my students, like Larry Brown, who actually was diabetic himself, would actually develop systems, in this case, for delivering insulin. So here we have a tiny system, no bigger than an aspirin pill, and you can take this and implant it in a rat and lower the blood sugar from 400, which is diabetic, to 100, which is normal, and keep it there for over 100 days. I'm going to come back to this point a little later to show you how you could regulate it. And this would begin to establish the in vivo feasibility of these kinds of things. Now, how could we get people interested, companies interested? Well, it really, when we do these things ourselves as professors, we always kind of think that what we're doing is important. And I would try to get people interested. And I could tell you, for the first 9 or 10 years I was doing this, absolutely nobody cared. And finally, at about 1983, 84, a Japanese company, actually Takeda, they called up and they said, well, we'd like to give you some grant money. Any professor hears that, that's, magic. But they said, what we'd like in return is we want to send a scientist to your lab each year. I said, that's great. And so actually they did that. But what they did is they actually then went back and they made actually the very first controlled release system for a peptide. And that's shown here. They actually developed a drug called leuprolide acetate. It's about 1,200 molecular weight, and it's a very powerful drug. But if they gave it by any conventional method, it was destroyed right away. So they put it in these little microspheres. And originally, they would last for a month. They were injectable. Now they actually have made them to last for 4 months. And today, this is actually the most conventional way of treating advanced prostate cancer, endometriosis, or precocious puberty. It's over $1 billion a year product. Now, to get people interested in protein delivery, that was even harder. So, and in fact, we couldn't get any company to be interested in that. So Alex Klebanoff, who was a professor of chemistry, and myself actually decided to start a company which would ultimately merge into Alkermes. And Alkermes, working together with Genentech, using this approach, basically developed the very first controlled release system for a protein. And this is human growth hormone, which normally you have to take once a day. Now you can take it once a month. And there are many, many others in various stages of clinical trials. There's one, again, by Alkermes that's at the FDA. It's gone through all the trials for schizophrenia, many others at various other stages. So basically, we've been able to get some of the fundamentals done to release these kinds of molecules at either decreasing or steady rates. But you always like to do better. And one of the things that I wanted to do was someday to be able to make these systems smart. Like, say, for that diabetic situation, could you ever release more drug when you want to? So a couple years ago, I was watching a TV show and I was watching a PBS show, and they were talking about how microchips were made in the computer industry. And so I started thinking, gee, this might be an interesting way to develop chemical delivery systems. So I called up Michael Sema, who is a professor in material science, and I asked him if he could help us. And what we came up with was this kind of design as a prototype. And instead of like a regular chip, this one contains real chemicals that you can store and release to the outside world. So here's the idea, that basically you have an impermeable coat down here, like an epoxy. You build little wells in, and you cover them with gold. This is a cutaway. You could, by the way, use various materials. You don't have to use these, but turns out these are pretty good in the body. At any rate, the drugs will stay in there for pretty much as long as you want, but if you apply just 1 volt selectively to any of these little micro-patterned wires, they will actually, as I'll show you, dissolve the gold, and then whatever's underneath it can come out. It'll come out right away if you put no resistance underneath it. But if I want to make it take longer to come out, I could put a polymer or gel or something like that and essentially, hopefully, get almost any delivery pattern. So I had a very good graduate student, John Santini, and he actually designed some of these. This one, what you're looking at is a United States dime, and these are the 2 sides of the chip. There's 34 wells on this. He's now made them. He actually has a company to do this, over 100 wells, and I think pretty soon will be over 1,000. Now, sometimes people ask, could you put much drug in these? The answer to that really depends on the clinical application. But a way of thinking about this is you could probably, let's say you could put a 1 cubic centimeter chip as an implant or a pill. Well, the way to think about that is 50% of the volume of the chip could actually be the drug. So if you make a conservative assumption that the density of the drug is the density of water, 1 gram per cc, that means you could put 500 milligrams of drug in such a system. What does that mean? 5,000 0.1 milligram dosages, or 500 1 milligram dosages, or 50 10 milligram dosages. That's a way that you might think about it. So we made these chips, and just to look at how they work, here's an example looking at, again, a micrograph of just a single well, and it'll stay like this for years. Hermetically sealed, the drug is in place. But if you just apply 1 volt to this, in 10 seconds, here's what happens. The gold comes off. And as soon as it does, the drug can come right out. So what we've been able to do is you could take 1 drug and deliver it in multiple doses. Here's an example where we've taken a single drug and arbitrarily released it at 1.5 days, all different doses in the well, at 1.5 days, at 2.5 days, 4.5 days, and 5.5 days. Each different well is a different amount. And again, these are purely arbitrary. We could have selected essentially any pattern we want. Someday, our thinking is that you could almost have a pharmacy on a chip. Let's say you wanted to deliver multiple drugs at multiple times. And as a prototype of that, John released multiple drugs here. And here what you're seeing is drug released at 2.5 days, another drug from a different well at 3.5 days, this same drug from a different well at 5 days, and this same drug from a different well at 6 days. Again, it's arbitrary. Now, since this time, we've also taken this in vivo in rats and done pretty extensive biocompatibility studies on these materials, and they seem quite safe in animals. Our long-range goals for this, which we're currently working on, are to see about ultimate applications in a variety of diseases. But some of the things that we've been trying to do are, could, for example, you deliver this by remote control, like by telemetry? So probably you could open these wells up by telemetry in much the same way you open up a garage door. You could open up any individual well whenever you'd want. Also, what we're trying to do is incorporate biosensors into these chips, along with a power source and a microprocessor, so that you could essentially have a direct feedback control system. Also, what we hope to do, since it's a chip, you could actually download the information that, whenever you deliver a drug, you could actually have the information be transmitted to your computer in your home, your doctor's office, or the hospital. So all these are going to happen in the future someday, we believe, and hopefully do some very useful things in medicine. Now, so far, what I've told you about is how we can kind of take materials and engineer them to do things they couldn't do before. But another concern I've had is the materials themselves. And when I was working in the hospital many years ago, I was very curious to see how materials would find their way into medicine. And being a chemical engineer, I guess I always thought that the driving force for bringing materials into medicine would be other chemical engineers that were before us, or chemists, or material scientists. But as I examined this, I found that was rarely the case. Almost always the driving force for bringing materials into medicine were like companies and very often clinicians. And what the clinicians would do is they actually wanted to solve a problem relatively quickly. And the way they would do it is they would go to their house and kind of find a household object that resembled the organ or tissue they wanted to fix. Let me explain that. And this is all true. I mean, people may think it's funny, but they're all true. So let me tell you about the artificial heart, which you read about a lot in the newspapers today, but you probably don't read about the origins of the materials so much. Well, the origins of all this started in 1967 at the National Institutes of Health. And there, some of the clinicians were trying to figure out how to make an artificial heart. And one they thought about from a material standpoint is something with a good flex life. And they thought, what object has a good flex life? And said, a lady's girdle. And they said, what's it made out of? Polyether urethane. So that's what they made the artificial heart out of in 1967. Problem is, that's what they make it out of in 2002 as well. And you could look at various journals like Time or Newsweek or scientific journals. It doesn't really matter. One of the biggest problems in the artificial hearts, it turns out the mechanical engineers have done a pretty good job. It beats long enough. But when blood hits the surface of the artificial heart, the lady's girdle material, it can form a clot, which could go to the brain, and the patient could get a stroke and die. And yet, if you think about it, something that was designed to be a lady's girdle might not be, the optimal material to put in contact with blood. And this problem pervades all of medicine. Dialysis tubing was originally sausage casing. Vascular grafts, that's an artificial blood vessel. That was a surgeon in Texas going to a clothes store to find what he could sew well with. And by the way, I don't want to minimize these approaches because they really enabled the first wave of progress to occur in the 20th century. But they also create problems, as obviously people know. You can't, for example, make vascular grafts under 6 millimeters in diameter because, again, blood sees an unnatural surface, it'll clot. The last one, I hope there are no lawyers here. But if you look at breast implants, one was a lubricant, and the other actually a mattress stuffing. I see people are thinking of the logic. But it's true. I mean, that's often how these things happen. So what we decided to do was take a very different approach in the 1970s. And that is, rather than take a material off the shelf, rather to ask the question, what do you really want in a biomaterial? From an engineering standpoint, from a chemistry standpoint, from a biology standpoint, and then could you synthesize it? So we picked an example, and that example had to do with biodegradable polymer implants. And when we started this work, there was only one synthetic polymer that had been approved by the FDA for implantation. Those were the polyester suture materials. And they dissolve like this, a process we call bulk erosion. So you uniformly distribute the drug in the system, but over time it would get spongy and could fall apart. And that's fine for some drugs, but it could lead to bursts of drug coming out, which, for example, if you had a really toxic drug like, say, insulin or an anti-cancer drug, this might not be so good. So we said from an engineering standpoint, what you'd like to do is surface erosion. That's analogous to the way a bar of soap dissolves or the way an onion peels. And if you could do that, the thinking was you shouldn't get this dose dumping. Not only that, the design should be very easy. If you want to double the lifetime of the device, you just double the thickness, for example. The challenge was how to do it. And we went through a pretty detailed engineering design analysis to figure out the right bonds, the right monomers, the right chemical structures. I won't go through all of that with you, but other than to show you the final answer we came up with is this shown by this chemical structure. It's the only structure I'll show. But it turns out to be a polyanhydride. That's the bond. And we picked two monomers, two units, one which is very hydrophobic to keep water out, and the other slightly less hydrophobic. And we based this particular structure on not only chemistry, but also toxicology. Michael Marletta, who was a professor at MIT at the time, helped us figure out what monomers would be safe in the human body. And so this was a hypothesis. But some of our students, like Howie Rosen, synthesized these polymers. And what we found, this was work by Janet Tamata, was that basically you can get, by simply looking at percent degraded or released, this is 0% sebacic acid, one of the units. This is 15%, 55%. The whole point is by simply adjusting the ratio of these, this a millimeter thick slab will take 4 years to dissolve. But as you increase it, it'll dissolve faster and faster. With 79%, you're all gone in 2 weeks. So you could simply dial in the ratio of these monomers, and it would last for whatever length of time you want. So that would give you the opportunity to design systems that could last anywhere from days to literally years. So I was going to tell you, we've actually over the years been looking at a number of applications. I thought I'd show one of them for you. This is brain cancer, glioblastoma multiforme. It's uniformly fatal, and regardless of how you treat it, the mean lifespan is less than a year. So so it's a terrible disease, and the drugs that you give, for this disease are really bad drugs, and they cause a lot of side effects. The major drug that's given is a drug called BCNU, shown here. And normally you give it intravenously, so it travels throughout the whole body, causing a lot of serious side effects on the liver, kidney, and spleen. So Henry Bremen Henry was a young neurosurgeon at the time. He's now chief, actually, of neurosurgery at Johns Hopkins. But he, in 1985, came to see me to see whether we could try to apply some of these ideas to treating brain cancer and actually more broadly other localized diseases, which I'll mention shortly. But basically the idea that we started talking about is, could you develop what we'll call local therapy rather than systemic therapy? And the idea was that you could operate, now in this case for neurosurgery, operate on the patient and take the tumor out, because you're going to do that anyhow. That's what the neurosurgeon would do. But before he'd close up the patient, he'd line the surgical cavity with the polymer containing BCNU. That's the drug. They wanted the polymer to be degradable so it wouldn't accumulate in the brain, to have the surface degrading property so it couldn't dump this toxic drug. And from animal studies they'd done, they wanted to last for a month. And you could do that with these polymers by simply adjusting the ratios of those units. At any rate, so the polymer protects the BCNU from degradation. So if the polymer lasts for a month, the drug will last for a month. But most importantly is this concept of local therapy. High concentrations in the brain where you want it, and low or almost non-existent concentrations in the rest of the body where it could cause harm. Now, whenever you get an idea and you're a professor, I mean, what you have to do is raise money for it. So we would write grants to the federal government, generally the National Institutes of Health, and our peers, my peers, would review it. And over the years, I actually saved a lot of their grant reviews, which were not particularly good. I thought I would show you a couple of them today. So I entitle this slide, "This Approach Will Not Work Because." And in 1981, when I first wrote about this is purely from the polymer standpoint, the chemists would look at it and they said, well, these polymers can't be synthesized. So Harry Rosen and Bob Linhart in our lab worked out ways to synthesize them. So then 2 years later, the reviews came back where they said, well, OK, they can be synthesized, but these polymers will react with any drug you put in there. So Cam Leung, another one of our postdocs at the time, worked out ways so that wouldn't happen by making salts and other things. So a couple years later, we wrote again. And they said, well, but these polymers are low molecular weight. They're fragile. They'll break up in the body. Can't be useful. So Avi Dome, another one of our postdocs, worked out ways, figuring out the right catalysts and time and temperature conditions in the synthesis to make them very high molecular weight and strong. Actually, all of these, by the way, made for great doctoral theses or postdoctoral projects. And all these guys actually became, that did it, like full professors today, different places. Anyhow, the next issue was, well, these are brand new materials. They're certainly not going to be safe in the body. But it turns out Cato Lorenzen, who was one of my students, did a lot of studies on animals showing that, in fact, they were. So finally, we're now in 1988. And this was not actually a review. I was running one of these conferences called the Gordon Conference, which are these conferences where you actually like to encourage a lot of discussion. So being a chemical engineer, I thought it would be fun to invite a lot of other chemical engineers. But I also thought it would be nice to invite Henry Brem, who's a clinician, because I wanted to show people how people were starting to think about this young field from a medical standpoint. So I asked Henry to give a talk, and he went over his talk where he was showing how he was treating this disease in animals. And at the end of his talk, the number of the chemical engineers raised their hand, and they said, well, Dr. Brem, that was a very nice talk, but we've developed these mathematical models that show that the drug will not diffuse far enough to kill the remaining tumor. I have to pardon our spelling. But at any rate, Henry then said, but I just did show that it killed the tumor. And the chemical engineer said, no, that's not important. They said the models show it doesn't diffuse far enough. And they kind of went back and forth about what was important. In fact, it wasn't until about 5 years later that Mark Saltzman developed some better models to predict this. The next issue was that even if it did diffuse far enough, it's not a very good drug. That, by the way, is true. And one of the hopes we have is that with this kind of approach, you could put much better drugs in. And the Hopkins group and others are doing that now with newer drugs like Taxol and cytokines and so forth. And the next issue was manufacturing, that this would be very difficult to manufacture. And Guilford Pharmaceuticals, which licensed it from MIT, worked those things out. And finally, in 1997, the FDA actually approved this procedure. It was the first time in over 20 years a new treatment had been approved for treating brain cancer. Now, actually, I'd like to actually show you what this operation looks like. But if anybody's squeamish and doesn't like the sight of blood, I'm really serious about this, you really shouldn't look at the next two slides. But what you do is these are going to be human patients. And here you put one little disc in the brain here. Usually you put 7 or 8 and then close the tumor site. You know, it's very hard to get good advice whenever you give a talk. But a couple years ago, actually, I was lecturing to a group of chemical engineers, and my wife, Laura, came to the lecture, and I asked her at the end of the talk, I said, what did you think of the talk? And she said, well, the talk was okay. That's actually very high praise. But she said, Bob, you know, you had those 2 bloody slides on for 12 minutes, and you explained every detail of the operation. I was kind of excited about it. You know, it was like our polymers going to people. And she said, you explained every detail of the operation. She said, I don't know if you were looking, but all those poor chemical engineers were turning green and looking at the floor. So ever after that, I've done just what I did today, but I do want to tell you the sequel to this. About 2 years ago, Mike Moskowitz, a friend of mine, he's a neurologist. He was running a conference called the Princeton Conference, and he actually asked if I would give the dinner speech. But you see, this conference is tended pretty much by neurosurgeons and a few neurologists. Now, there's all clinicians. So I gave them the same talk. I told them the same story. And at the end, a number of the neurosurgeons came up to me and they said, you know those 2 bloody slides you showed? I said, yes. They said, you could have left those on as long as you wanted. They said, that was fine. But they said, those chemical formulas. That's also true, both of them. And so now when I give the talk to neurosurgeons, it's very different, you know, about what I put on. At any rate, to show you a little bit of the clinical data, I mean, this is by no means a cure, but there is improved safety and efficacy. And what you see is if you look at the treated group at the end of a year, you see about 63% survival in the treated group, 19% in the controls, and at the end of 2 years, 31% in the treated group and 6% in the controls. And it does relieve suffering as well. Now, and like, as I mentioned, the FDA has approved it for different uses. Now, you know, whenever you do something like this, there's different milestones that maybe you hit. You know, one, we were excited when we synthesized it. Another, when it first went into people. Finally, when the FDA approved it. But about a year and 3 months ago, I found something out that I guess I hadn't expected, which was that it actually got onto national television. And I'll tell you a story on this for those of you that aren't familiar with this. So there's this TV show. I don't usually watch it, but it's called ER. Some people probably do watch it. And it turns out that the star of the show is a guy named Anthony Edwards, and he plays this clinician named Mark Green. And he has a brain tumor. By the way, for those of you that don't watch the show, if you ever watch this movie Top Gun, that stars Tom Cruise, and he's Tom Cruise's partner in that. He actually didn't do too well there either. But at any rate, so what happens in the show is he keeps, you know, looked like he had a very bad brain tumor. He was going to be off the show in about 2 weeks. So he'd go from doctor to doctor, and they all would tell him, you know, he's off the show in a couple weeks. And finally, he goes to one last doctor, who actually turns out to be Susan Sarandon's husband, I mean in real life, or ex-husband in real life. But anyhow, this guy, when you see him, and I'll show you this video clip in a second, you sort of get the impression he may have gone to Harvard Medical School. You'll see what I mean. At any rate, so I'm going to show you this video clip from ER. See if this works. Here he is.
What did he say?
I think it's trial.
That you're going to be able to settle.
Yeah, so did I. Rachel called. She wants to come out a day early for Christmas.
Mark Green? Dr. Burke, nice to meet you. You too. And you are?
Dr. Elizabeth Corday, Dr. Green's fiancée.
Oh, congratulations.
Thank you.
Sorry to keep you waiting. I met some resistance in tumor board. Is that good or bad? The oncologists and radiation therapists are having trouble embracing the future.
Meaning?
Come over here. They see a lesion like yours, they jump to the conclusion it's inoperable.
But it's not.
Not in my hands. There's your tumor. Now, as you were doing verbal tasks, there was increased blood flow to language centers. Those light up in orange. Now, as you can see, while the tumor's adjacent to Broca's, it hasn't invaded yet.
That's what the neurosurgeon in Chicago said.
That's why you're here.
So you'll operate?
Yeah. We'll do an awake craniotomy. You'll be conscious and talking while I map out Broca's and resect the tumor. But the real bonus is my ability to insert high-dosage chemotherapy wafers into the tumor cavity and use the malignant cells themselves to create a cancer vaccine.
Thank God for second opinions.
Yeah. Those idiots in the tumor board are satisfied with 12-month survival. Where most of the patients on my protocol are disease-free for 24 months and counting.
When can you fit him into the schedule?
How about December 31st? You can ring in the new year with a load off your mind. Brain surgeon humor.
Right.
You okay?
Yeah, sure. It's good news.
It's very good news. You came to the right place, Mark.
So anyhow, the bad news about this is that it looks like now he wants to get off the show, so they, you know, it's about a year and a half later, so his tumor may be coming back. But you see, that would actually probably mimic what may happen in real life. These treatments extend life, they relieve suffering, they probably double lifespan, but they're not a cure. And so the hope is by finding better drugs and better materials, we'll be able to do better still. Also, one of the exciting things about this is now many groups are extending it into other areas. So there's actually already another localized tumor, spinal tumor that's been approved, another one for ovarian cancer is in clinical trials, and it's being extended to other areas as well. Like one of the big areas, which has been very exciting, is in the whole area of heart disease. One of the most common ways of treating heart disease is to use balloon angioplasty to open up a blood vessel, but the blood vessels close off over about 6 months, so people put in stents. These are little, like, Chinese finger puzzle things. The problem even there, about 25% of the times the vessels close off and the patients die. So what they're now doing, and Johnson & Johnson's probably the leader, but about 5 companies have done this, is develop, again, this whole idea of localized chemotherapy right to the blood vessel, keeping the blood vessels open with really, actually 100% open after the 6-month time period and greatly increased survival. And I think, again, it's only the imagination of clinicians that as people move forward to think about other applications one might use. The next example I wanted to use is actually, it's an interesting personal story. You know, about 7 years ago, I had a postdoc come to me named David Edwards. Actually, Bob recommended him to see me. And David actually had already done one postdoc and actually had never done experiments. He was a chemical engineer, extremely bright, but always had done mathematical modeling. And in fact, the very first time he came to our lab, the first paper he wrote had 300 equations in it. But then we got him interested in thinking about other delivery problems, and one of them was to the lung, and I'll tell you a little bit about that. Right now, when people take aerosols, and probably different people know people who've taken meter-dose inhalers or nebulizers, you generally have, it's unbelievably inefficient. You're lucky if you get 5% of the drug from the device into the lung. The reason for that is you've got these tiny aerosols, usually liquids, and they've got enormous surface area, so they aggregate. It's kind of like wet sand. In fact, more recently, people have even come up with dry powder inhalers. But because aerosolization is so inefficient, I'd say over the last 10 years, we've seen about 40 different companies develop better, through mechanical engineering, better aerosolizers, better devices. And the reason they do that is because if you could make them better, maybe you could go from like 5% to 8% or 9%. That's pretty much what's been done. And that would mean you'd save a lot on the drug, but also you could make the device a lot smaller. People want to use these for insulin and other things, and you don't want to carry around a giant inhaler. But David came up with a very different way of looking at that. He said everybody else has looked at the device. Nobody's looked at the aerosol. And you might think, well, how could you redesign water or other aerosols? But see, what everybody had been doing was designing these tiny aerosols. But what David thought is, what if we make really big aerosols? But unlike regular aerosols, and first of all, why might bigger be better? Well, the idea bigger could be better because they wouldn't aggregate as much, right? There's a lot less surface area. So if you think about it, wet basketballs aren't going to aggregate like wet sand. Also, we thought that when they went into the lung, they might get cleared a lot more slowly because, see, the clearance mechanism are macrophages, these cells, and now they're sort of seeing a big meal rather than a small meal. They'll just take longer to eat it. But if you made a big aerosol, the conventional wisdom is it won't work. It'll settle in the back of the throat. So what David did, he did a lot of modeling studies, came up with the idea he'll make a big aerosol, but make it incredibly light. In other words, everybody had made before aerosols with a density of 1 gram per cc, like the density of water, whether it was a liquid or a powder. He said, well, let's make the density 0.1. And what Jeff Herkash and others in our lab did was come up with ways to make these aerosols. And if you think about it, what they're going to look like, see, a regular aerosol looks like a little golf ball or a little baseball. What we're now doing is making wiffle balls. And so they made these. And what was really exciting about them is you could take a conventional inhaler, and this is in vitro. If you looked at the regular aerosol, you get about 5 or 6% in. David's aerosol, you'd get about 60% in, 10 times more. That's in vitro. If you go in vivo and you look at the different lobes of the lung, what you see is each time, and you have the same number of particles, you get about 10 times more particles deposited with the porous ones than the non-porous ones. If you translate that to the amount of drug that goes to the human body, let's take insulin, it turns out that if you use a control or non-porous one, you basically get almost no insulin level. But if you take an injection and compare it to the porous ones, in a single whiff, you get 86% of the drug that you'd normally get by an injection. And if you make the aerosols a certain size, here, a single whiff of insulin lasted 4 days. And David actually, with a number of our students, started a very successful company, Advanced Inhalation Research, based on this. And in fact, for the people who invested in that, they actually, for those of you that follow business, they actually made a 1,000-fold IRR, which is an annualized return. So they did pretty well. And, but basically what he was able to do in starting this company, which is now part of Alkermes, is make aerosols. And here is one of them delivering for 3 days. And about 8 different ones are now in clinical trials. So people are using this now for asthma drugs, for insulin in clinical trials, human growth hormone in clinical trials, and many others. And actually, one of the nice things that's interesting is David ended up making a reasonable amount of money for this and actually ended up buying a building on Boylston Street right opposite the Boston Public Library and set up this foundation. It's like a 4-story building for teaching poor kids in Boston arts and dance and things like that. So it's actually a very nice personal story to see him go all that way. And actually, he was elected to the National Academy of Engineering at the age of 39 for this. Now, the last thing I wanted to talk about was possibly creating new tissues. Let me motivate that by showing you a child who has liver failure. That child was a patient of my close collaborator, Jay Vacanti. And the problem is when somebody has a problem like liver failure, the only way a child like that can live is somebody else has to die. And then you do a transplant. And that's what Jay does. But the problem is, take liver failure, there's a giant donor shortage. Last year, 30,000 people died of liver failure. There are only enough donors for 10% of those. And so because of that, Sammy, you got to. My 8-year-old son is coming to the lecture. He wants to be an engineer someday. So, but he's asking his mom questions. So, at any rate, and actually, what he wrote when he had to do his autobiography was actually very interesting. When he was 7, he wrote to the teachers, when he grows up, he's going to be an engineer, and then on weekends, he's going to go to take his children to MIT and show them his lab. I don't know where he got that from. So, at any rate, so because of that, Jay and I came up with this idea that maybe you could take isolated cells. In fact, we were doing a lot with stem cells, which I didn't put up here. But you could take stem cells and convert them into the right cell type. And then what we wanted to do is have like a polymer scaffold. And again, I'm not going to go into all the engineering of it, but the idea is if you could put the cells close enough together, several groups, like Basel's group at Berkeley, have shown cells are smart. And so if you take mammary epithelial cells, put them close enough together, they can actually form acini and make milk. And so what we did is we wanted to create polymer scaffolds with the right signals and the right proximity to allow the cells to reorganize, grow them in a bioreactor, and then ultimately make a new tissue. This was the idea. Now, to do this, we could make polymer fibers, which you see here, with liver cells on them. And actually, you can, Prasad Chastri in our group actually worked out ways to make them in almost any shape. So here's a shape of a nose. And someday you might envision using like computer-aided design, CAD/CAM techniques, like if somebody wanted a nose, like say an upturned nose or hook nose, you could make almost any kind of nose you want. And make it into a so that was the idea. But let me illustrate some of the challenges in tissue engineering and why it's a bit different than other fields of just cell culture. So I'll pick the idea of making new blood vessels. And this was the work of several people. But first, one of the challenges, this is to make very small diameter blood vessels, which had never been done before. So one of the challenges is to make little tubes, 3 millimeters in diameter. Dave Mooney, one of our graduate students, who's now a professor at Michigan, did that and made these tiny little tubes. Then Jinming Gao, who was a chemist from Harvard, George Whiteside's lab, and now a postdoc with me and now a professor at Case Western, then worked out ways to alter their chemistry of the surfaces of these polymers in such a way you could get a high cell attachment. Then Laura Nicholson, who really led this project, she was an MD PhD, now she's at Duke, she actually wanted to mimic a real blood vessel. So what she'd do is put smooth muscle cells, those are the cells that are in the outer part of the blood vessel, and then endothelial cells, which are on the inner side, that's the EC of the blood vessel. But the real trick to this, see, if you've ever gone to a biology lab or a medical lab and you look at how they grow the cells just sit there. Maybe there's a mild shaking or whatever, but they pretty much sit there in an incubator or a shake flask. And nobody could ever get this type of stuff to work. A few people even did flow. But what Laura said is, you know, that's not what's happening in our body. Our body, they're not just sitting in an incubator. What happens is they're actually hooked up to a pump, you know, your blood vessels in the body. They're hooked up to a pulsatile pump, your heart. So she actually created a whole cell culture system very different than before, where she'd actually create bioreactors in such a way that she would make these tubes be exposed to pulsatile radial stress. And in particular, the design she developed is shown here, where she figured out the right medium. Here's a pump that will beat at 165 beats per minute like an embryonic heart, right into these little vessels over an 8-week period. And at the end of that, you get these tiny little vessels like this. And if you examine them, they have all the characteristics of a regular blood vessel. The same amount of collagen. They're actually quite strong, which had been a big challenge before. They can withstand 2,000 millimeters of pressure of mercury. You can actually suture them into an animal and keep them there. And they have the same pharmacology as a normal blood vessel. And you could take the toughest animal model, a pig, and by doing angiography, you can keep the blood vessels open for months. One of the big challenges is getting enough of a cell source of the endothelial cells. And recently, Shulamit Levenberg in our lab actually worked out a way to, using human embryonic stem cells as a starting point, work out ways to actually now make endothelial cells in large quantities. And the hope is at some point this could go into humans. A second example I wanted to pick is cartilage. There's over 1 million operations each year where people need new cartilage. And our idea, in fact, this is already being done now, we're working on this clinically, is you could take a few cells from a patient, maybe from their ear, by an arthroscopy. And then you could make a scaffold in any shape you want, and it shouldn't reject if they're their own cells. So Chuck Vacanti, one of our collaborators, actually did this on nude mice where it shouldn't reject. And here he redid this guy's skull. Here, he redid this guy's cheek, the top guy. And if you open the animals up, they have the same, they have white glistening cartilage. It has all the biochemical characteristics of cartilage. It, by the way, is not perfect. It doesn't have as good a mechanical strength as normal. In fact, Lisa Fried and Gordana Vanyak-Novakovic in our laboratory are working on ways of using bioreactors to, again, sort of like the blood vessel work, to apply the right stresses so that someday maybe we can do things where you can have the right mechanical loads. But even so, you can begin to think about using these for plastic surgery. So Linda Griffith, when she was a postdoc with us, we were working in this case with Joe Upton, who's a plastic surgeon. And he sees children that don't have ears. So he wanted to make a new ear. So Linda actually worked out a scaffold in the design of a human ear. Here's a scanning electron micrograph of it at very high magnification. These fibers will ultimately dissolve, and you'll ultimately get tissue here. And Chuck Vacanti, who collaborated with us at UMass, actually didn't put these on humans, but did put them on rabbits. And here is the rabbit with the human ear. And you might ask, why do we do this to rabbits? But the reason we do it to rabbits is, of course, someday we want to do it to people. And this was the first patient. It's a 12-year-old boy. This is a number of years ago. But if you look at him closely, notice he has no chest covering his heart. But like other 12-year-old boys, he likes to play baseball. But if he were ever hit in the chest with a baseball, he could die. So actually, Jay, my collaborator, operated on him. We made a scaffold to make a new chest for him, took his own cells, and actually did make a brand new chest. Now, a couple years ago, after this was done, Business Week decided to do a big front-page feature on tissue engineering. And inside, they actually featured this child who was then 16 years old and 6 feet tall, skateboarding. Now, none of the clinicians liked that, but the point was he was doing fine. And we've begun applying these to many other areas as well. Also, what we've wanted to do, MIT is a terrific technology transfer office, so we've licensed our patents to a number of companies and tried to work with them in different ways. One of these companies have actually now gotten approval using these polymer cell approaches to actually make new skin for burn victims, and this is now FDA approved. Let me give you a very positive example of that. So here you're going to be looking at a 2-year-old boy who's badly burned. But what you can do is take this system, which is a polymer scaffold with neonatal dermal fibroblasts, put it on the child at the time of injury. Now let's come back 3 weeks later. And now let's go back 6 months later. So this is just an example of what we hope to see happen someday, more widespread, but it gives you an idea of what can happen here. Now, the very final example I'd like to do in terms of closing the talk is spinal cord repair. Here, Erin Levick, one of our graduate students, has been working in material science, has actually worked very closely with Evan Snyder at Harvard Medical School. And what she wanted to do here is actually design a polymer that was very much like the spinal cord. So she created an outer portion that, using different material science techniques that could provide axonal guidance, and an inner part that was very porous that you could actually put what's called neuronal stem cells in. Let me show you a little bit about what they look like. So here's the scaffold. It's like a little cylinder. Here's the porous part on the inside. Here's the oriented part on the outside. So here's the animal model we used. She actually would make paraplegic rats, did about 50 of them. And there's actually ways to quantitate this, but I'm just going to show you a video. And what she did is she took out a portion of the spinal cord. And the idea is that would make the rat paraplegic. She did controls where she'd put the scaffold by itself, where she'd put the cells by themselves, or just nothing. And then she would insert, this is a 4-millimeter system right in the defect to see what would happen. Now, these couple of caveats, these defects are, none of these models are perfect. First, the rats. Secondly, we're putting these in within 24 hours after injury. But what I want to do is now show you a video just of actually one of the average controls and one of the average experiments to show you what these look like about 70 days later. So here's a control. Focus on the hind legs, where it's, like I say, paraplegic. He's going to be dragging them. And also notice the paws. If you quantitate this, this guy probably has a BBB score of about 5. Again, he's paralyzed. Okay, now we're going to go to the experiment. And here's the experiment where notice the hind legs and also notice the paws. So this is about a 13. It's not a cure by any means, but certainly he's able to walk much, much better. And like I say, there's about 13 experiments, about 37 controls. Again, focus on the appearance of the paws as well. Okay. So again, this is a very early stage, and it's animals, not people. But again, I think it fits sort of what I hope the title of the talk meant. And that's sort of how I'd like to end this, that we've probably raised a lot more questions than we've answered. There's a lot of things, and I think that's one of the great things about MIT, where there's just so much important research to do. There's so much we don't understand about these areas. At the same time, we like to think that at least this field has moved a little bit further, and that people are beginning to start to use principles like this in ways that can begin to relieve suffering and prolong life. Thank you very much.
I'm sure Bob would be glad to take
absolutely.
a few questions if there are some. Yes.
Can you talk a little bit about your philosophy for conducting research? How do you go about finding problems that are crucial problems that you think people need to work on? And
Sure.
Yeah.
Well, that's a great. We choose problems. You know, I guess what I've tried to think about as I've thought about projects over the years was something that, on the one hand, would be at a relatively early stage, you know, that in other words, but to pick a kind of idea that would almost be a dream idea, but that if we were successful could have a profound impact on things in the future. And so it leads to the kinds of problems that I guess I would sort of could lead to what I'll call sort of a core technology. You know, it's interesting, if I look at almost every one of the projects that we talked about, like releasing large molecules, the first time I thought, well, maybe we'll be able to release insulin someday. Turned out still not releasing insulin clinically. But because we kind of established a lot of basic principles, it could be used for a lot of things. Same thing with tissue engineering. You know, the original target for that was treating liver disease, and we're not even close. But the fact is that because these principles are there, we or others can begin to think about treating a lot of diseases. And I think that that's largely what we've tried to do, is try to pick problems where we can maybe do some research at an early stage that, if it's successful, opens the door for us and others to think about you know, many, many different directions.
Yes, up in the back.
On that chip when it's in the body.
Right, so the question is, how can we apply a voltage to the chip when it's in the body? So again, there's several levels of this. In the early studies, what we've done is simply use wires and have them come out. But in the long run, what we do is basically it's the same way you open up by telemetry. In other words, you basically would have a little microprocessor power source on the chip that you could just activate by remote control. So you'd have all those units in the chip, and they're actually being built right now. Like I say, it's pretty standard electrical kinds of approaches. Any other questions?
Let's thank Bob again.
Oh.
There's one more.
You're a PhD in chemical engineering to doing a postdoc in a hospital. Seems like a large jump, at least at that time, to most people.
Yeah, well, that's also an excellent question. You know, it's interesting. When I look back to my career and my degree of uncertainty about what I wanted to do, I got my degree in 1974. And at that time, almost all there was sort of this energy crisis, supposedly. You know, if you had a car then and you were waiting, you'd have to wait 2 hours in the gas station to get gas in line. And that's what a lot of my friends did. And I remember thinking about doing that, but I just had trouble getting excited about, I guess, working in an oil company. No, I mean, it wasn't that bad, but I mean, I remember going to Baton Rouge and other places and thinking about it. And I really didn't know what I wanted to do. You know, I actually applied. I was very interested in teaching chemistry education. I'd spent a lot of time as a graduate student helping get a school started for poor kids and working on chemistry education. I applied to a lot of schools like City College in New York and even actually some pretty crummy schools, and they actually wouldn't even look at my application. You know, I really was interested in doing that. Finally, and I applied for some faculty positions, but I thought my ideas at the time, even though I got a couple of offers, were not very good ideas. So I didn't do that. And finally, so I finally started thinking about maybe working in a hospital, because I was always interested in maybe trying to do some things that I felt would help people. And also I was interested in learning some biology. And so one of the postdocs in my lab at the time, Barry Bunow, actually suggested writing to Judah Folkman, and you know, so I did. And when I went over to see him, I mean, it's kind of the lowest paying job by far, but I was really excited about his ideas and about the possibility of doing something in that area, and so that's what I did.
Thank you.